So today we're going to be solving Schrödinger's equation in 10 lines. So to start with, I want to do a quick overview, and then we'll go into each line in more detail. So to start off with, we start with our imports, then we define a few variables, then we define some diagonal matrices, then we will define our D parameter, which involves these sparse matrices, then we will create our kinematic energy variable, which will have these Kronecker sums that we'll talk about in a little bit. Then we have to create our grids, that's going to be our X, Y, and Z. Then we will create our potential. So our potential in this case is going to be the harmonic oscillator potential, and so that has these square terms. Then we simply put it into the SciPy solver. That will give us eigenvalues and eigenvectors, and then we have a wave function from. So the eigenvectors correspond to wave functions with the energy of the eigenvalues. In the upper corner, we're going to try and highlight the portion of the Schrödinger equation that we are actually focusing in on at the moment. And so hopefully that'll help give you an idea of how the code and the analytical formula overlap. Okay, so going into more detail, the variables that we're defining on the second line are going to be the size of our grid that we're using, so that's the large N, physical distance, and the small n is how many eigenvalues you're calculating. So these are going to be the smallest energy values. For the second line, this is creating a diagonal that has this many indices, so this is going to be ones that are 30 long. And then for the second one, you're just creating n by 3 matrices that will have these things, and what we're eventually going to do is we're going to put this into a sparse matrix. The next line is basically pushing them so that they will be on the diagonal. And so now we get to the Kronecker sums, and this is the part that might throw people off a little bit. So when you're thinking about doing this in 3 dimensions rather than 1 dimension you don't need Kronecker sums, but once you get to 3 dimensions, you want to put all of your values onto the same matrices so you don't have to do very complicated math. And so how you can do that is you can use a Kronecker sum, and that basically just combines these grids so that they are linked together in the proper way. Next step is a very straightforward grid creation, and then we will create the potential with the values from the grid, and that we will reshape into a diagonal that we will add to our kinetic energy, and this is the eigenvalue problem that we're going to solve. So now we've transformed an analytical problem into a really high large matrix problem. For this particular case, it's 30 cubed equations that we have to solve. Luckily, computers are insanely fast, and this actually can get solved in like a second, which is mind-boggling. But anyway, the fact that you can solve like 100,000 equations in less than a second is just ridiculous. So the actual plotting for this came from 2 videos we had previously done. So the one on hydrogen atom was where most of the plotting came from. And then the interactive chart aspect comes from the 5 simple projects that we previously done. So if you're curious about the code in the actual plotting in augmented reality, that's where we get that from. Plotted on a glass grid instead of a square grid so that you don't end up with the fringes that square grids tend to have. But one of the things that brings up is that the process of getting it to a glass grid actually doesn't conserve probability. So you'll end up having to renormalize it or some other thing in order to get it to be a probability of 1. So you shouldn't do the math on the glass grid. And once it is in a glass grid form, it like kind of invalidated aspects of the math. But for visual purposes, it worked really nicely. There's this non-peer review paper that summarizes this process very nicely, and so it was something that I used quite a bit of, so that is the source that I used. It's not peer-reviewed, but I've done most of this process before from peer-reviewed sources in longer form, so not without using the sparse matrices and some of the other methods. This is a very common thing that you do a lot, but I just thought this unpublished, or this non-peer-reviewed paper was really well written, so if you have any difference, that's a good source. Famously, the ground state of most quantum systems has a non-zero energy, and so we can see that here with the harmonic oscillator. And the harmonic oscillator is used as a foundation for a lot of other systems. So if we get into quantum field theory and things like that, it uses a lot of the same mathematics. And so you end up with a ground state that has non-zero values. And so when you talk about quantum fluctuations and things like that, a lot of that has to do with overlapping non-zero ground states of miniature oscillators. And so this oscillator model is actually heavily used, although it's usually the one-dimensional oscillation, but it is heavily used in other areas because the mathematics is simple enough that it can be abstracted into very distant topics. So thanks and have a good day.